Thanks for tuning in to this revision zone video of the energetics topic. We're going to be looking at bond enthalpy within this one. So we're going to be looking at definitions and how to calculate the enthalpy change. So we're going to look at definition to start with. Now, the definition of bond enthalpy, there are two definitions you need to know. We'll look at both of those. So the definition of bond enthalpy is the energy required to break 1 mole of a particular bond in a substance which is in gaseous state. It's quite important, that gaseous state. And this links to the enthalpy of atomization, which we'll look at in later videos. And we, of course, have to have our 1 mole in every time. Now, we don't use a bond enthalpy to calculate the enthalpy change. What we do use is we use the mean bond enthalpy instead. Now, unfortunately, I can't just take one bond enthalpy of a particular molecule and use that everywhere in my calculation. Because the bond enthalpy or the energy required to break a particular bond, let's say a CH bond, changes from molecule to molecule because it is dependent on the environment it is in. Now, we are going to use an example here, and I'll use methane as an example. But the definition for mean bond enthalpy is the mean value of energy required to break still 1 mole of a particular bond, but taken over a wide range of substances, again in gaseous state. So what I mean is a CH bond in ethane, a CH bond in methane, a CH bond in ethanol will all actually have different enthalpies or bond enthalpies, and as a result we have to be careful that we can't assume that they're all the same, and therefore we take an average. So what we're going to do is we're going to look at methane as an example to try and illustrate that. So here we've got methane. Now you can see methane here. Now methane has 4 carbon-hydrogen bonds. Now in this particular case we can assume, for instance, for now, that each of these are the same. You might think that initially anyway. But in fact, if I was to take one or break one carbon-hydrogen bond, so this bond here, okay, to form this and this, so again they are still in gaseous state, so the methyl molecule there and a hydrogen atom there, that will have a specific enthalpy. Let's just call that delta H1. The next one, so these are successive, so if we successively break each carbon-hydrogen bond, so we will try and break the second carbon-hydrogen bond here to form this molecule here, and another hydrogen atom, will not be the same as delta H1, it will be a new enthalpy. And we can keep removing those carbon-hydrogen bonds as we go down in successive stages, and that will change each time. This just illustrates that the bond enthalpy, or the strength of the bond, is determined by the environment it is in. It is not static, no matter what molecule it is in or at any point within the molecule. So that is something that we need to consider. So we must take a mean bond enthalpy. And it's not an average of all the bond enthalpies of carbon-hydrogen in the world. Is of an assortment of molecules. So let's have a look at how we're going to actually use these mean bond enthalpies. Now, in order to do that, we really need to look at what do we mean in terms of enthalpy, the direction of energy change when we break or form a bond. Now, the first one here is bond forming. So what we need to understand is when we're forming bonds, it releases energy. So I'm just going to write releases energy here. And releasing energy means that it's leaving the system. So we say that it's exothermic. That energy is leaving the system into the surroundings, so it's exothermic. And we should know that the enthalpy change for this will be negative. So keep that in mind. It's really quite important that we understand that it's a negative enthalpy change. The direction of that energy is being is going from the system to the surrounding. Next, bond breaking, maybe a little bit easier to get your head around if you struggle with this, but bond breaking absorbs energy. And that means you're adding energy into the system. So a classic analogy for me, at least anyway, on this to help students understand it is if I'm trying to break a chocolate bar, I'm going to put energy into the chocolate bar to actually snap it. If you break anything, you're putting energy into it. So that means that this process is endothermic because you're adding energy into the system. And we should also know that the enthalpy for this is positive. It's really quite key. Just make sure you remember these two. That negative for exothermic bond forming, bond breaking is endothermic, and you add energy within the system. It's also important to know that if I have a carbon-hydrogen bond here, or in fact, let's take something different. Let's take an OH bond. If I say an OH bond, get a different color pen for you. So if I take an OH bond, the enthalpy change for an OH bond is 463 kilojoules per mole. Now, if I was to break a OH bond, that will be positive 463 kilojoules per mole. It has to have a plus sign. I need that direction. If I was forming the very same bond, it's exactly the same amount of energy, but negative. So again, just make sure you know how to use those. They'll normally give you a book, either a book of data or a table with those values in, and those values won't have a sign in front of them. You just need to put those signs in front. Right, so let's have a look at how we can calculate this. So we're going to use bond enthalpies, like I mentioned before, bond enthalpies, yes, to calculate enthalpy changes. Now, up until this point, we've looked at using Q equals MC delta T to calculate enthalpy changes, or Hess cycles, as long as we know other enthalpies like enthalpy of formation and combustion. But we can also use bond enthalpies. Now, because it is a mean bond enthalpy, that means it's an estimate, it's an approximation. So as it says here, we can calculate an estimate for the enthalpy of a reaction or enthalpy change, especially for those we are unable to do experimentally. So it's quite useful. It's in fact very useful for us, especially if it's a reaction we can't do. However, there are issues. There are really quite some serious issues with it that we must consider, and something that you may be asked about in the exam. So the issues is the variation of bond strength. Now, bond strength is important because the actual bond enthalpy or bond strength is affected by the environment it is in. Okay, so is affected by the environment it is in. Now, what I mean by that is, as I've mentioned before, is that the bond strengthening of carbon hydrogen will be different in ethane, methane, ethanol, any other organic compound, or any compound you will find carbon hydrogen bonds in. Okay, so it's really important that you understand that there is a difference there. So that means that even though I'm using the average bond enthalpy, like let's take oxygen and hydrogen, 463 for an oxygen hydrogen bond, it might, and I'm looking at ethanol, it might actually be close, but it won't be exactly the same as the one in ethanol. So again, we need to be careful. The second one is that they are not necessarily in gaseous state. So for instance, if I do a reaction experimentally, combustion of ethanol, well, ethanol is liquid to begin with, so it's not in gaseous state. So if any one of my reactants are not gaseous, then they'll start to be an error or a deviation from the bond enthalpies that we use. If any one of my reactants or products are not in gaseous state, then we start to deviate, or there'll be a bigger difference between my bond enthalpy values when I've used those to calculate my enthalpy change compared to actually doing it experimentally. So for instance, like I've left a gap here. So if, as an example, if you were to burn ethanol, it would be a liquid, and oxygen gas, and we get CO2 gas. We normally write this equation with H2O liquid, but it would actually be gaseous, so that would actually work for us. But if any one of these reactants or products were not gases, there would be a greater separation of the values. And we can see here that is liquid and this is not balanced, but we can go away and balance that. So let's have a look at an example. Now this is an example from actual exam question here. We're going to work through it. So it's just, I've cut a few things out just to make it simpler, but calculating the enthalpy changes using bond enthalpies. Now, like I said, mentioned before, you normally get a table like that in your exam, and you can see that there are no signs there either. Now we're going to use that data to calculate the enthalpy change of the following gas phase reaction between hydrazine, N2H4, and hydrogen peroxide, H2O2. And they're given you the reaction here in the form of displayed formula. So it does highlight where those bonds are and what type of bonds there are. So it does make your life a little bit easier. Now, typically when I'm doing this, I look at putting this imaginary line down the arrow and it separates my bond break into my bond forming. And what we're going to do is we're going to have a look at working out the sum of bond breaking and the sum of bond forming. So in order to do this, let's just start with the reactant side. It needs to be balanced. It's already been balanced for us here. So we're going to use this here. So let's have a look at the first molecule, my hydrazine. My hydrazine has one nitrogen hydrogen bond. So I look at my table and I can see that it's 163. So we represent our bond like so. It's just one lot of that. You don't need the 1 times in, but I will do that. That's 163, and that is in kilojoules per mole as it states in the table. I'm not going to write that in until the end. I then look at the same molecule and I have 4 nitrogen hydrogen bonds. 4 nitrogen hydrogen bonds. That means 4 times nitrogen hydrogen. Now the nitrogen hydrogen bonds is 388, so it's 4 times 388. So this is in the first instance when I'm explaining to people, this is the method I use, and you will, if you've already done this and just using this as revision, then you will have come across an equation, and I will look at that at the end. But as I go along, I always tell my students to write down the values as you're working it out. And that shows the examiner exactly where your values are coming from. The next one I need to look at is the other reactant molecule here. Now I'm going to ignore this 2 for now in the balancing, but I can see I've got 2 OH bonds. I'm just going to stick to the OH bonds for now. So I'm going to write OH there. Now I've already got 2 of those, so I'm going to put 2 times, but I have 2 hydrogen peroxides molecules. So that's 2 lots of 2 OH bonds, so that I'm going to times that by 2, which essentially means that I've got 4 lots of OH bonds, and that 4 lots of OH bonds goes to 4 times 463, and again I'm going to show you what that amounts to, is 1,852. Now the next one and the last one on the reactant side is the OH, sorry, not the OH bond, the OO bond, the OO single covalent bond, which is 146. And I have 2 molecules of hydrogen peroxide, so it actually comes out as 2 times oxygen-oxygen bonds. So that's 2 times 146, which equals 292. Now what we're going to do is we're going to find the sum of all of these values here. So we'll write the sum of bond breaking. And that equals 3,859 kilojoules per mole. Now it is bond breaking, so we need to make sure we've got our sign there. So just stick your sign in. Just do that as a matter of course, and then you're less likely to make mistakes in other areas if you always think sign in units every single time. So we've done our bond breaking. We're going to now have a look at bond forming. Right, so bond forming are these 2 molecules over here, and you'll notice that we've got 4 lots of water. But we'll start with the nitrogen molecule. Now we've only got 1 lot of those, and nitrogen molecule has a triple covalent bond, and you can see it's the largest value in our table. And it would make sense to say that a triple bond is stronger than a single bond. And this is one of the reasons nitrogen is quite unreactive. It takes a lot of energy to get it to react. So I'm going to write 1 times. Again, you don't need the 1 times, but we'll put it in. And that equals 944. I've got no multiplication to do there. Now here I've got 2 OH bonds for every water molecule. So 2 times OH bonds, but I have got 4 lots of waters. So it's 4 times those 2 lots, which is essentially 8 lots of my 463. Now this is a multiplication, so I want to write my value in there. It's quite a large value, 3,704 kilojoules per mole. Now what I need to do again is I need to add these 2 together. So the total, so in fact let's write sum of bond forming is equal to 4,648 kilojoules per mole. But it is bond forming, which means I need to put my minus there. So my sum of all my bond formings is always going to be negative. Oh, sorry about that. So I'm going to put a little negative sign in there. Okay. Now if I add these together, I'll end up with my overall enthalpy change, which I have written here as 3,859 with my plus, minus, because it's exothermic, the bond forming process, at 4,648 kilojoules gives me an overall exothermic value of minus 789 kilojoules per mole. Make sure you're always putting signs in. Now you will have realized that, especially if you've done this before, is that the enthalpy of reaction is therefore the sum of bond breaking minus, because we're now looking at it being exothermic, the sum of bond forming. So that essentially is the overall equation for calculating the enthalpy changes using bond enthalpies. And it's this one that you commonly come across in texts. That concludes this video on bond enthalpies. If you like the video and you want to keep up to date with our new videos, hit the like button and subscribe, and we'll see you next time.